share, listen to Aloore Radio on Facebook. Aloore Radio, the voice of Oyo State. Gẹ́gẹ́ bí ìwòye àwọn òmòye tó ní òye bó ti yẹ kí ìlànà ètò ẹ̀kọ́ tó tó gbangba sùn lọ́yẹ́ orí gan lóde òní yàtọ̀ fáwọn ẹlẹ́bọ̀wọ̀wọ̀ tó lùgbòrò pa lórílẹ̀‐èdè yìí lọ́wọ́lọ́wọ́ báyìí ẹ̀sìn tó ń síwájú ọ̀hún rèé ilé ìwé Monarch Model College Challenge nìbàdàn àwọn ọ̀jọ̀gbọ́n onímọ̀ nípa ọ̀rọ̀ ìlànà ètò ẹ̀kọ́ nílẹ̀ yìí àti lókè òkun ló kórajọ pọ̀ síbẹ̀ àwòsífìlà làwọn èlò ìkẹ́kọ̀ọ́ ìgbàlódé tó sọnù síbẹ̀ àyíká ilé ìwé ọ̀hún rẹwà púpọ̀ ẹ̀rọ CCTV kámẹ́rà ń bẹ ní yàrá ìkàwé pẹ̀lú akẹ́kọ̀ọ́ péréte ní kíláàsì kọ̀ọ̀kan àwọn èlò eré ìdárayá tó kójú owó àwòmọ́ lè lọ lóríṣiríṣi àwọn akọ́ṣẹ́mọṣẹ́ olùkọ́ tó kójú òṣùwọ̀n ní kọ́mọ lọ́dọ̀ wa yàrá ìkọ́ ìmọ̀ ìjìnlẹ̀ sáyẹ́ǹsì tó sọ wọ́n nílẹ̀ yìí gbà ọmọ kan kọ̀ǹpútà kan ní bẹ́ẹ̀ lọ́kọ̀ bẹ́ẹ̀ tí ń káwọn akẹ́kọ̀ọ́ wa láàárọ̀ lọ́sàn-án lójoojúmọ́ pẹ̀lú owó iléèwé tí ò gún pa rárá ayò nílé ìwé yìí jẹ́ fún gbogbo òbí àtàlágbàtọ́ ètò ìgbaniwọlé lọ lọ́wọ́ báyìí o sí ẹ̀ka ti JSS 1 to 3 àti ti SS 1 to 2 Monarch Model College wà ní plot 86 and 87 Polariwa Street Police Post Challenge Ibadan 08169799661 website www.monarchmodelcollege.org Monarch Model College nìbàdàn ibùdó ìmọ̀ fáwọn afàṣẹwà lẹ́yìn ìwà ọ̀la.
Welcome to Monarch Model College, a community of kings and queens. We are located at plot 86 and 87 Polariwa Street at the back of Equa Church, Challenge area, Ibadan. You are welcome to our Teaching on Air episode for this week.
And the topic I have before me this afternoon is symbol, formula, and equation. So we start with chemical symbol. Chemical symbol. Bacillus in 1814 was the first scientist to suggest the symbol of an element. What is the symbol of an element? Symbol of an element represents an atom of an element. When we talk about the symbol of an element, it is just a means of identifying these elements. Bacillus suggested that some atom of elements should be represented with the first letter of the name of the element as given above. Now we see on the board that there are some elements that have the first letter of the name as their symbol, as in the case of hydrogen H, boron B, carbon C, nitrogen N, oxygen O, fluorine F, phosphorus P, sulfur S, vanadium V, iodine I, and uranium U. Since we have over 118 elements on the periodic table, and each of the elements on the periodic table can't be represented using the first letter of the alphabet alone, he further suggested that the first and the second letter, or the first as well as the third letter of the alphabet, should be adopted as given above. Bacillus suggested that some elements should be named using the first letter as well as the second letter of the alphabet. He represented the first letter of the alphabet using a capital letter, then the second letter of the alphabet he used a small letter, as in the case of helium, He, lithium, Li, beryllium, Be, neon, Ne, magnesium. On getting to magnesium, Bacillus represented the symbol of this element from the first as well as the third letter of the name of the element. Magnesium, he represented it using Mg. Aluminium, he represented it using Al. Chlorine, he represented it using Cl. Argon, Ar. Calcium, Ca. Bacillus further suggested that some elements should be represented using their Latin name. As in the case of sodium, the Latin name is natrium and the symbol is Na. Potassium, He further suggested that we represent potassium as K, and the Latin name is Kalium. Iron, ferrum, which is the Latin name, and the symbol is Fe. Copper, coprum, the Latin name coprum, and the symbol Cu. Silver, argentum, and the Latin name, argentum, the Latin name, and the symbol is Ag. Tin, the Latin name is tannum, and the symbol is Sn. Antimony, the Latin name is tibium, and the symbol is Sb. Gold, aurum, and the symbol is Au. Mercury, hydrogyrum, and the symbol is Hg. And the last but not the least on the list of bacillus is plumbum, which represented using Pb. We move to chemical formula of compounds. Now, when we talk about the chemical formula of compounds, we talk about a molecule of an element or a molecule of a compound. A molecule of a substance is represented by its symbol, by the symbol of the component element. For example, say oxygen. Oxygen, O2. A molecule of oxygen consists of 2 atoms of the element oxygen. A molecule of ozone, O3, consists of 3 atoms of the element oxygen. A molecule of sulfur 8 consists of 8 atoms of sulfur, while a molecule of hydrogen consists of 2 atoms of hydrogen. This is just a means of representing the molecule of an element using the component element consisting of that molecule. I said earlier that it is possible for us to have a molecule of a compound. Take, for example, sodium chloride, NaCl. Now, if you look at the chemical formula of this particular compound written above, you observe that though I have a molecule of that compound, I have 2 different component elements making up the molecule of sodium chloride. And as written above, you observe that I have sodium atom and chlorine atom coming together to form a molecule of this particular compound named sodium chloride. I can have a molecule of tetraoxosulfate 6, which is H2SO4. Now, in a molecule of tetraoxosulfate 6 acid, I have 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen put together to make up the molecule of tetraoxosulfate 6 acid. Now we move to the symbol of all the component elements given above. Compounds and the chemical formula. Sodium triioxocarbonate 4. Now, in triioxocarbonate 4, you see that I have 2 atoms of sodium, carbon, 3 atoms of oxygen put together to form the molecule of that compound. Copper 2 oxide, I have copper and oxygen. Sodium hydroxide, I have sodium, oxygen, hydrogen put together to form 1 mole of that particular compound. I have zinc 2 sulfide consisting of zinc and sulfur. I have zinc carbonate making up of zinc, carbon, and 3 atoms of oxygen put together to form zinc 2-trioxocarbonate 4. And the next I have ammonia, NH3. A mole of ammonia consists of 1 atom of nitrogen and 3 atoms of hydrogen put together. Then I have my potassium hydroxide consisting of potassium, oxygen, and hydrogen, making a mole of potassium hydroxide. Potassium chloride, I have potassium and my chlorine atom making up a mole of potassium chloride. The next I have valencies of elements and radicals. Now when you say valency, valency is a combining power of an element. I start by the definition of the element, valencies of elements and radical. Valencies is the combining power of an element, while radical can exist as an atom or a group of atoms that react together and behave as a single entity. Now, under the valencies, we have what we know as oxidation number. Now, oxidation number is the charge an atom of an element appears to have according to some set of arbitrary rules. Now, we'll be made to understand that metals exhibit positive oxidation number. I'm going to tell you the reason why metals exhibit positive oxidation number. Let us take, for example, sodium metal with the symbol Na and an atomic number of 11. Now, we write the electronic configuration using the KNM, KLM. And we'll be made to understand that each of these shells have a specific amount of electrons that they can contain. For example, the K shell can take a maximum of 2 electrons, the L shell will take maximum of 8, and the remaining 1 electron enters into the N shell. Now I said earlier that the metals, they have positive oxidation number. And coming back to sodium, you observe that the N shell, which is the valency shell, has 1 valence electron, and this valence electron can be given out in the course of electron transfer in the formation of bonding. Now, when this 1 electron is given out, it makes sodium to migrate to an ion, meaning that the neutral atom has given out 1 of its valence electron to become an ion, and in this particular state, it becomes excited, having a positive oxidation number. And I defined the other time that oxidation number is the charge an atom of an element appears to have according to some set of arbitrary rule. Now, from what I just did on the board, the oxidation number of sodium here is +1 because the 1 valence electron has been given out in the course of bonding. Another example is aluminium with an atomic number of 13. And when we write the configuration, we have 2, 8, 3, meaning aluminium has 3 valence electrons on its outermost shell that can be transferred, that can be given out for formation of bonding. So in some cases, you see aluminium ion written as Al3+. Now the 3+ represents the valency or the oxidation number. And don't forget, metals have positive oxidation number because oxidation simply means loss of electron. And from what I have on the board, you observe that the element gives out or loses 3 out of its electrons, making it migrate from the neutral point, that is 0 state, to +3. Increase in oxidation, positive oxidation number. So metals exhibit positive oxidation numbers, while non-metals exhibit negative oxidation number. Let's take, for example, chlorine with an atomic number of 17. Chlorine with an atomic number of 17. Now, when we write the electronic configuration, we are going to have KLM with 2, 8, 7 electrons. Now, looking at chlorine, you observe that the valence electron is lacking or deficient of one electron. And according to the octet rule for stability, we've been made to understand that the maximum number of electrons that a shell will accommodate is 8. And if you look at the chlorine atom, you observe that it has not attained the octet state. So chlorine will invariably be looking for an atom of an element that has excess of electron that it can gain electron from. So we need one valence electron to add to the self-valence electron of the chlorine atom to make it attain the octet state. So the moment the chlorine atom gains that one electron to itself, it becomes chlorine ion with a negative charge. This negative charge means that one electron has been obtained from other atom of an element to make this negative sign. So in this particular state, we say that chlorine has a negative oxidation number, an oxidation number of -1, because this is a sign of reduction. Because reduction simply means a gain of electron, while oxidation means losing electron. So, and chlorine happens to gain one electron to itself. So, in this particular state, I will say that the valency of chlorine is -1, and the valency of sodium is +1. Now we proceed. For example, let's take oxygen again. Oxygen has an oxidation number of -2. Now, if you look at the atom of oxygen with an atomic number of 8, we have 2, 6 using the KLM representation. Now, if you remember the other time I said the octet rule for stability, that the maximum number of electrons that a shell will take is 8. Looking at oxygen, you see that the valency shell needs 2 more electrons. So in this particular state, I say that the oxidation number is -2. And in some cases, it will be represented as O2 minus, meaning that 2 valence electrons has been obtained in order to attain the octet state. Now, oxygen exhibits 2 oxidation states. The first oxidation state is -2, and the second oxidation state is -1. Now, the -2 oxidation state is when you have a compound in a binary compound. Say, for example, sodium trioxocarbonate 4. Now, the oxidation state of oxygen in sodium trioxocarbonate 4 is equal to -2. But in situations where you have your peroxide, like sodium peroxide Na2O2, hydrogen peroxide H2O2, the oxidation number of oxygen there is -1. Unlike in your binary compound where you have the oxidation number to be -2. Now we proceed to elements, the symbol and their valencies. Aluminium, the symbol is Al and the valency is 3. Argon, the symbol is Ar and it has no valency. Now there's a reason for that no valency. Now going by argon, on the periodic table, the argon has been placed in a special class or group which we call the group 8 or O of the periodic table. Now, if you look at the periodic table, the group 8 or O, we have helium, neon, argon, krypton, xenon, radon, and gases, organeson. Now, looking at these elements, there's a special name that we give to them. We refer to them as inert gases, noble gases, or rare elements. Why? The other time I said that the valency shell, that is the octet state, the maximum number of electrons that a shell will take is 8. And And if you look at the argon, going by the atomic number, argon has an atomic number of 18. Ar is 18. Writing the configuration, we have 2, 8, 8. And according to the octet state, the valency shell is full. In this particular state, I say argon is stable. Why? Because it can no longer accept electron to itself and it cannot give out electron. That is, the valency shell is completely filled with electrons. So in this particular state, you say that argon is stable because there is no way it can take any other electron to itself. So as a result of that, it does not have any valency, no oxidation number. We say zero valency or zero oxidation number because the valency shell is completely filled with electron. Now going by barium, Ba, the valency is 2. Bromine, Br, the valency is 1. Calcium, Ca, the valency is 2. Carbon, the valency, the symbol is C and the valency is 2 or 4 because carbon exhibits 2 oxidation states. It's either you have carbon 2 oxide or carbon 4 oxide. So carbon exhibits 2 valency, which is carbon 2 and carbon 4. Chlorine exhibits 1 oxidation state, which is 1. Copper, 2 oxidation states, copper 1, copper 2. Gold, 1 oxidation state. Helium happens to fall in the same family as argon. So helium does not have any oxidation state. Hydrogen, H, oxidation of +1 in a binary compound, then -1 in an hydride. Say for example, you have sodium hydride. Fine, there is a particular set of rules you obey when you are calculating oxidation state or oxidation number. Now this is a binary compound. So the algebraic sum of all the elements in a binary compound equals 0. To ascertain what I just said about the oxidation state of hydrogen in an hydride. Don't forget the other time I said the oxidation state of sodium is +1. Plus, since we are calculating the oxidation state of hydrogen, we can represent it with X. Then you equate everything to 0. Now, in the course of doing that, you just say X equal 0. By the time the +1 moves or crosses the equality sign, it becomes -1. So you have X equal -1. And I've told you the other time that the oxidation state of hydrogen in your hydride is -1, except when hydrogen is in a binary compound. That's when it exhibits an oxidation state of +1. Then the next one is iodine with an oxidation state of 1. The next one we have iron with an oxidation, 2 oxidation states, +2, +3. You can have iron 2, tetraoxosulfate 6, iron 3, hydroxide. So we have 2 oxidation states. Krypton, no oxidation state or no valency or no oxidation number because it falls under the same family with your helium. Then lead with 2 oxidation states. We have lead 2 and lead 4. Now we move to valencies of some radical. Don't forget I told you the other time I said radical exists when 2 or more elements react and behave as a single entity. Now you look at ammonium. Ammonium is NH4+. NH4+. And the valency there is +1. As written on the board, the valency is +1. Hydroxide, OH-, with a valency of -1, dioxynitrate 3 -1, trioxynitrate 5 -1, trioxocarbonate 4 -2, tetraoxosulfate 6 -2. Now this leads us to writing formula from valencies. It is possible for us to write formulas of compounds from their valencies. Let's take for example, example 1, the formation of sodium chloride. The formation of sodium chloride. Going by it, you see that I have sodium ion and I have chloride ion. And the valency of sodium ion is +1. The valency of chloride ion is -1. Now, since the charges are equal, the charges cancel. So we are going to have NaCl, and the name is sodium chloride. Sodium chloride. We move to the second one, which is the formation of ammonium tetraoxosulfate 6. The other time I said ammonium ion is NH4+, tetraoxosulfate 6 ion, SO4 2-. The valency is +1 and the valency -2. Now you ignore the charges and you exchange the valencies. So 2 goes to ammonium and the 1 goes to tetraoxosulfate 6 as written above. Ammonium tetraoxosulfate 6. Then we go to formation of iron 3 tetraoxosulfate 6. Our ion is Fe3+, tetraoxosulfate 6, SO4 2-. The valencies here +3 -2. Ignore the charges as earlier said. Exchange the valency using the crisscross method of formula formation. Then you have Fe2, open bracket, SO4, close the bracket, 3-. And that gives us iron 3 tetraoxosulfate 6. Now with their explanation, the above explanation I have just given, I would like us to proceed further by doing the exercises. Now the first exercise, number 1, we have copper 2 ion and an hydroxide ion. We want to form a compound and name it according to the Ibadan nomenclature. From these, we be made to understand that the valency here +2, the valency -1. I said earlier that you ignore the charges, then you exchange the valencies. You are going to have Cu1, open bracket, OH, close bracket, 2, which is the same as writing Cu, open bracket, OH, close bracket, 2. If you want to name this is named copper 2 hydroxide. Copper 2 hydroxide. I move to the next one, which is ammonium ion tetraoxosulfate 6 ion. The valency here +1, the valency -2. I ignore the charges, I exchange the valencies. Open bracket NH4, close bracket 2, SO4. This is ammonium tetraoxosulfate 6. Ammonium tetraoxosulfate 6. Then we move to the third exercise. Cu2+, PO4 3-. Valency +2, -3. I ignore the charges and I exchange the valencies. I have Cu3, open bracket, PO4, close bracket, 2. I have copper tetraoxophosphate 5. Copper 2 tetraoxophosphate 5. Then we move to the next one, which is the last, but not the least. We have ammonium ion and tetraoxophosphate 5. So this is +1 minus 3. We ignore the charges and exchange the valences. Open bracket NH4 close bracket 3 PO4. So we have ammonium tetraoxophosphate 5 compound. So this with these I've come to the end of the class for today. Any question? Yes.
We're talking about
tetraoxophosphate 6 ion. Yes.
And they said sulfate is 1. Or sulfate. Sulfate is 1. Why can't we add this to those instead of tetraoxophosphate 6? Why can't it be tetraoxophosphate 7?
No. Tetraoxophosphate 6. We have two, like I rightly said the other time. I said we have two oxidation states, that is +2 and +6. So when you talk about the tetraoxophosphate 6, the sulfate 6 there is in its +6 oxidation state. Now the -2 oxidation state we talk about is when you have sulfur gaining electron from an atom and element S2 minus. This is sulfide ion, like I rightly said. And normally we said sulfur has an atomic number of 16, that's 286. And according to the octet, we need 2 electrons to attain the octet state. So it accepts 2 electrons. This is a sulfide ion. The sulfide ion is not the same thing as your tetraoxophosphate. There's a difference between an ion and a radical. This is mainly your sulfide ion, while in that particular state I talked about the other time, it is your radical because it's a component of 2 elements reacting as a single entity, not just an entity as stated in your sulfide ion. Thank you. Any other question?
What is copper? So why do some of them say copper and iron when copper and iron is like 2?
Thank you. Now there is a universal, I call it IUPAC nomenclature. IUPAC stands for International Union of Pure and Applied Chemistry, and there is a system of naming that is universally acceptable by IUPAC. You don't just start like copper hydroxide 2. No, because it is the copper that has that oxidation state of +2, not the hydroxide. Because the hydroxide is a radical, is acting as an anion. And an anion cannot have a positive valence. So it is named copper 2 hydroxide, not copper hydroxide 2. Thank you. Question? Okay, your question again.
How many radicals do you have in chemistry?
Okay, how many radicals? We have a lot of radicals. Over 1,000. In as much as we have over 118 elements on the periodic table. These elements can come together and react, especially when we have chemical combination or bonding. So you can have as many radicals as possible in chemistry. We don't have a specific numbers of radicals. We have a lot of radicals. Thank you. Any other question? Your question.
Can we add any other elements to add PO4.
Can you add
Another element to PO4.
yes? That was what I did. I have an aeon. I reacted it. I exchanged the valencies with my PO43 minus because my PO43 minus is a radical. So, and I have an aeon together with a radical by exchanging the valencies to form my compounds. Yes, it is possible for you to add other elements with your PO43 minus. Any other question? With this, I've come to the end of this.
Thanks so much for joining us for this week. Have a pleasant week ahead. See you next time.
Oh yes, your long-awaited Citadel of True Education for the Rare Gems, Monarch Model College Challenge Ibadan. Intelligence with good character makes up the real goal of true education. Parent and guidance, connect your child to the arena of kings and queens, where quality and sound education is undoubtedly available. It's a government-approved school that stands tall, among others, with the best and globally acceptable standard of teaching, beautiful and hygienic learning environment, professional subject teachers, well-ventilated classrooms with small class size, ultra-modern science laboratory, standard music lab, standard computer laboratory, maximum security with CCTV surveillance. School buses are also available, all with affordable school fees. Admission is ongoing into GSS 123 and XS 122 classes. Application forms are available at Monarch Model College, plot 8687 Polariwa Street, behind Egoa Church, Police Post, Challenge Ibadan. 0069799661. Website www.monarchmodelcollege.org. Monarch Model College, a community of kings and queens.
Share, listen to Aloore Radio on Facebook. Aloore Radio, the voice of Oyo State.